Hey, today we're going to see how to calculate a standard deviation using a simpler method than the traditional method. Once again, really quickly, what we did last time is calculated a standard deviation using the traditional method, which is to take the literal average of the deviation scores. Once again, all that means is that we figure out the difference between each individual score and the mean. Simply subtract the mean from every individual score. Then we squared those differences so that we got rid of all the negative values. Otherwise, we always get a standard deviation of 0 forever because all of the differences to the right of the mean will cancel out all of the differences to the left of the mean. And so we have to square those values in order to get rid of the negative values. Or we could just take the absolute value, but that is a little more tedious. So anyway, then we get the average of the squared differences, but then they're still squared, so we have to take the square root of each of those, of the total. Then we get the actual standard deviation for our sample. Now that's all fine and good. That's perfectly logical to do that. It just takes kind of a lot of work. So today I'm going to show you the method to do it with just a few steps. So we'll see how that goes. All right, here's the simplified equation. It kind of looks like a lot, but it's really fewer steps. I promise I'll demonstrate that. Here's the equation. Okay, so all of this is familiar. Essentially, this shouldn't be terribly surprising, but I'm going to walk through each one of these relatively quickly. Now, it's important that you're going to arrive at the exact same answer as you would using the other equation. In other words, this one is mathematically equivalent to the other equation. It just uses fewer steps. So I'll show you how that works. First, let's compare the two equations so that we can get a better look at what's going on differently in both of these. Okay, so here on the left was the original equation. That's the one we did in the last video, right? You had to calculate the mean, subtract it from every instance we had an observation of the variable that we were looking for. In other words, each score. Then we squared the difference between that score and the mean. Then we added up all those squared differences and then divided by n minus 1. Why it's minus 1 we'll talk about at a future date. You don't need to worry about that. Or you can read my textbook, obviously. Maybe we won't talk about it at a future date. Maybe you should just read the textbook. It's not terribly difficult. Anyway, so that's a lot of steps. In this new one, however, it actually turns out it's fewer steps. It may look like more symbols, but fewer steps. So one thing you'll notice in this newer version is we don't have to calculate the mean at all. We don't have any bar x's, right? This is the symbol for the mean. We don't have that. We have x sub i's. That's the same thing as we had before, and we just have fewer steps. So again, let's now dissect that newer equation. Okay, so here's the newer equation. Once again, we've seen all of these symbols before. The capital italicized n just means the total number of times that we observed a value of our variable. Or in other words, it's the number of people that we have in our data set or the number of rows that we have in our table. If you prefer to think of it that way, that's perfectly fine. X sub I means every value we have of that variable, right? So every value that we have of whatever variable that we're using. Very straightforward. And then the sigma is the Greek letter that means you add up whatever is next to it. It's the total sum of whatever's next to it. So now let's break this down just a little bit more because this is the most important thing about this equation. I've taught this course for more than 10 years, and this is one of the #1 mistakes that students make is confusing these two things. So I'm going to spend some time on that now. Okay, so I've color-coded them to hopefully make it a little bit easier to tell the difference apart. Now you'll notice the only difference here between these two things is that this one has parentheses around the sigma x sub I, whereas this one has 0 parentheses. Now what that tells us is we do whatever is in the parentheses first. That's order of operations law. You should know that from junior high, high school kind of stuff, okay? You do whatever's in the parentheses first. Now you notice if this one doesn't have the parentheses there, that means that we rely on the order of operations. And in this case, the order of operations dictates that exponents come first. So therefore, rather than addition, which would be the sigma, we square everything first. Okay, so that's exactly what the issue is. This green one then tells us to square each value of x first, then to add up all of those values of x. And that's exactly it in plain English if you were to translate that. A nice way to remember that is that's called the sum of squares, okay, meaning that you have to square it first, then sum the squares. So this little green guy here is the sum of squares. Now in contrast, the purple value that I have color-coded here in purple means that you first do what's in parentheses, add up every value of x that we have, then you square that sum. Okay, you add up the entire, all of the x values you have, then square whatever you end up with. Some students will confuse these two, they'll switch them around, or they will treat them as if it's the same thing, and it is not the same thing. For example, if you add up all of the x values, then square them to get this guy, and then you think, oh, this is the same thing, right? I just square what I just calculated. That will get you the wrong answer, so do not do that. Make sure that you know the difference here. One is to square the values first, then sum them, and the other is to sum them and then square them. All right, so now let's see how this goes. We'll use the same data as we had in the previous lecture so that you can see that we arrive at the exact same number. So again, what I said here is that our little scenario was that we were planning some kind of party and we wanted to see how many people were likely to show up. So this was the data that we were using. And again, this is just a made-up scenario. Again, 7 years isn't a lot of data to deal with, but if you have no other information that would help you estimate, this is fine to use. Okay, so let's start here. So in other words, in year 1, there were 32 people. In year 4, there were 61 people. What I'm trying to get at is not only how many people should I expect on average, right? That would be the mean. But what is the likely variation from that mean that I'm likely to see? In other words, what's the likely maximum number of people I should expect? And what's the likely minimum number of people I should expect? That's what I get using the standard deviation in addition to just my measure of central tendency, in this case, the mean. Let's try it out now with the equation. So I've got the equation up here and the steps that we're doing I've got in red so that we can keep better track of it. Easiest thing to do here is to find n. Capital italicized n, of course, is the number of observations of our variable. Our variable was how many people showed up, and we observed a value of that variable 7 times. As you can see here, we had 7 years in which we observed a value of the variable number of attendees. So n is going to equal 7. There you go, n equals 7. So now n equals 7, I can replace these n's in the equation now with 7, which I'll do now. So there they are, replaced with the 7's. Now I've got an actual value instead of a symbol. That's fantastic. Now all I do is I find the sum of the x values. That's the next easiest step anyway, and so I'll go with that. We'll do it just in the parentheses. It says add up all of, the little I means all of, the values of x. Okay, that's easy enough. My x variable is these guys, so I simply add all of those up. And here's what we get. So 32 plus 45 plus blah, 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 do the whole thing is 335. Right, now, you'll recall that we had to do this anyway in the previous equation because I had to find out the sum of the values in order to get the mean in the first place. Then the next step in the previous equation would be to subtract the mean from every value. But I don't need to do that in this one, so we'll just carry on. Anyway, so now we have here 335 is the total of the x variable. So I'm going to replace this red text here in the equation with 335. I'll show you that on the next slide. Right there. So you've got 335 there. My capital italicized n's are now replaced with 7's because that's that value. Now here's what we don't have. This is the only piece left, is we need to square each value of x, square each value of x, and then I take the sum of those values. So first I'll square each value of x. That's easy enough. I square 32 to get 1024, square 45 to get 2025, square 42 to get 1764, and so on. Okay, so if I square each of these values, I'll put their squared value over here. As you can see, I've got x squared. This is x squared sub I, in other words, every one of them. Now the last thing to do is to sum those, right? I already summed the values of x to get 335. That goes right there. And if I sum up all of these squared values of x, I get 16,557. I'm sorry, 577. Now you'll notice 335 squared is not 16,577, which is why we do both of these, okay? These are not the same thing. Once again, 335 squared is not 335. I'll show you that next. Yeah, that's what we just did. So here's what we have now. We can plug everything into the equation, right? We found the sum of the sum of squares was 16,577, and this is the sum of the x variable. Now, if we square that sum, we get 112,225. Okay, you'll notice that's different from this value, quite a bit different. So once again, I can't overemphasize this. Do not treat the sum of squares and the square of sums as the same value. It's not the same value. Okay, so now we just continue on with that. We squared that to get that, and I subtracted 1 from 7 to get 6. Now we'll keep going on in the next slides to simplify this. Okay, the 112,000 whatever divided by the 7 gets us to 16,032. Let's make a quick note here. As you're checking your math, this value must be larger than this value. It absolutely has to be. Potentially they could be 0. They could be the same, I mean. They could be the same. But this value has to be bigger or equal to this. It can never be smaller than that. And that should make sense because if we get a negative value in the numerator, we can't divide, we can't take the square root of a negative number. Our calculators will explode. Not really, but don't trust me, it doesn't work. So that's it. So our difference between that and that is, of course, 544.86. And this, at this point, we now have exactly the same equation as we had in the previous one. Okay, so 544.86 divided by 6 is, of course, 90.81, the square root of which is 9.53. So that is our standard deviation, is 9.53. And you'll notice that's exactly what our answer was using the previous, more complicated but traditional equation. So what this tells us is that our average was 47.86, and we knew that from the last equation. We didn't calculate the mean in this particular one. And now we again confirmed that the average difference from 47.86 in the number of attendees we had was 9.53 attendees, average difference over the years. And then we interpret it the same way. So if again you're not sure how to interpret it, you could just go back and look at the same response or the same ending, the interpretation of the previous video, and it's the same interpretation. So that is that. That's a much simpler way to get our standard deviation, and it's a perfectly legitimate way to do that. So once again, the standard deviation is the average difference from the mean. We just used a simplified version of how to do that. It helps us to know how precise of an estimate our mean is of the population parameter of the central tendency, and specifically the mean. Yes, this simplified version is very nice because it takes out some of those extra steps. We don't have to go row by row and subtract anything from anything else. What's nice about it is it arrives at the same answer. So use whatever you're comfortable with to arrive at the same answer, unless, of course, your instructor tells you specifically use the raw score version versus the computational version. And here's a tutorial for how to do that. Once again, I cannot overemphasize, do not mix up the the sum of squares versus the sum of the square of the sums. They're very different. This is a very common mistake for students to just treat them as if they're the same thing, but they're different steps. Okay, that's it for now. We'll cover more things next. I'll see you then.